Right, so our last section for this week will be 3.5. Okay, it's on finding roots, not only that are real, but now we're going to look at roots that are imaginary, okay, or complex. Imaginary numbers are kind of one of those things that they're not used often. Okay, if you're asking where you're going to use imaginary numbers in your daily life, for the average person, no. The average person doesn't use complex numbers in their daily life. Sure, I could go online and try to look up some examples where you'd use them, like in engineering. I know there's some, but unless you're going to be an engineer or one of the few fields that uses complex numbers, there's not a lot of real-world applications that are simple that most people do every day. Okay, so we're not going to do a lot of word problems with this. Okay, mostly it's just to look at how we use complex numbers, but not as much application in this section. All right, so remember the idea: if a number is a root, you plug it into your function and you get 0. Okay, we've written this at least 3 or 4 times by now. Okay, that's also the same thing as saying you have an x-intercept at that point, which is also the same as saying x minus c is a factor. Okay, but this is the one that we're going to kind of focus on right now, this idea of crossing the x-axis. All right, so as long as your root is real, okay, it's a real number, you can see it on the graph. You can look at it, it'll cross the x-axis, and there's a root. But just because it doesn't cross the x-axis doesn't mean there's not a root. Right? Roots can be imaginary. And if they're imaginary, you're not going to be able to see them on the graph. Okay, we have to solve it algebraically. Okay, like this one. Okay, y equals x squared plus 1. Okay, what am I doing to this parabola? The basic parabola would be y equals x squared. But what does the plus 1 on the end do? Aiden?
It's going to shift it up, so it's not going to actually touch the x-axis on the graph.
Right. This is not going to touch the x-axis. So what that means is there's no real roots. Okay, but it doesn't mean there aren't imaginary roots. Okay, there is a way I can plug something in for x and get 0 for y. It's just not a real number. Okay. So remember, for imaginary numbers, okay, we start out with this definition. Okay, I equals the square root of -1. Okay, this is not something I could prove to you. This is just a fact we just start with. It'd be kind of like in geometry. If I said to you, parallel lines don't cross, and you said, well, prove that. Well, I can't. That's just a basic fact that they define parallel lines or two lines that don't cross. Okay? So we got to have some basic facts in every subject we don't explain. They're called postulates in geometry. Okay, this is kind of like a postulate in algebra 2, or an axiom. Just I equals the square root of -1. And from that, we'll build other things off it. Like I squared. I squared would be I times I. Or we could write it as the square root of -1 times the square root of -1. What is that? Yeah, it's -1. Think of it as the square root of -1 squared. It's one way to think about it. Okay, so you take I and you square it, you get -1. Well, let's see what happens if we plug I into the equation we just had on the other page. Okay, let's plug in I for x. Okay, we would get I squared plus 1. Okay, I squared plus 1. What did we just say I squared is? Okay, what's -1 plus 1? 0. So I is a root in that equation. Okay, I is a root. Anything you plug in and get 0, it's a root. But it's not a real root. It's a complex root. And one thing about imaginary roots is they always come in pairs. You will never have an odd number of complex roots. If there's one here, there's another one. Okay? Negative I would also work. All right? If you plugged in negative I, you would have negative I squared plus 1. But when you square a negative, what happens to it? Yeah, it cancels out. So basically, we're just left with I times I again. Okay, so that's negative 1 plus 1 gives me 0. So negative I is the other root. Okay, and those are the only two roots this one has. No real roots. Just I, negative I, the complex roots. Okay, any question on that? Yeah?
For a second, so did you just say negative I squared equals negative 1?
Negative I in parentheses squared does equal negative 1. Yes. Yep.
Okay. Okay, yeah, it's just confusing because you put negative in front of the I and it makes it out. So it's a singular I, which is in turn negative 1.
Think of it like this. Think of it as negative I times negative I. What's a negative times a negative? Positive. And what's I times I? I squared. So when you multiply negative I times negative I, the negatives just cancel. And it's the same as I squared.
I know, I just forgot for a second that I equals negative 1. I have no idea how.
I squared equals negative 1.
I squared.
Yep. All right, so complex numbers, we usually write them in the form a plus bi. Okay, so we have a real part and then an imaginary part. Okay, the real part is a, the imaginary part is b. So here's some examples of complex numbers. Okay, 3i, negative 7i, 4. Okay, 4 is considered a complex number. 2 plus 3i, that's a complex number. And 2/5 minus I. If we take a look at 3i, okay, 3 is the imaginary part. What's the real part here? The number 3i. What is it? Yeah, you could think of it as 0 plus 3i. So if I asked you what the real part is, well, there isn't one. It's just 0. How about negative 7i? What's the real part there? Connor? Yep, so it would be 0. These first two are examples of pure imaginary numbers. They don't have real parts, called pure imaginary numbers. Okay, how about the second one, 4? What part is it missing? It's missing the imaginary part, so what would that be? Yeah, you could think of it, if you want to write it as 4 plus 0i, you could. The real part's 4, imaginary part's 0. Okay, the next two actually have both parts. Okay, in 2 plus 3i, your real part is 2, imaginary part is 3. The next one, the real part is 2/5. What's your imaginary part here? Negative what? Just negative 1. Okay, the real part and imaginary part are just numbers. Right? The I is next to the number to tell you which part is imaginary. Okay, so in this case, there was no number. You could write it in if you want. Negative 1i. Okay, so imaginary part, negative 1. Any questions on that? Okay, we're just going through the basics of complex numbers. There's a lot to complex numbers. You can basically do a whole class on it. You can take a whole class in college that all it is complex numbers. Next year, you may take calculus, okay, at Monty Tech. Well, you can also do calculus again with complex numbers. So complex numbers really double everything you can do. You can do things with them, you can do things without them. Okay, but we're just covering some of the real basic stuff. All right, for two complex numbers to be equal, okay, two things have to match up. The real part of the first number has to match the real part of the second number. And the imaginary part of the first number has to match the imaginary part of the second. So here's an example of two complex numbers that are equal. 3 plus 2i and 3 plus 2i. If I change part of it, let's say 3 minus 2i, these would not be equal. The real parts match, okay, but that's only half of it. The real parts have to match, and the imaginary parts have to match, okay, for two complex numbers to be equal. All right, so we'll look at a few quick rules for arithmetic, okay, mainly how we add, subtract, multiply, and divide. And then we'll start to get into the actual how do we find roots with complex numbers. Okay, a couple things that'll be helpful is treat I like a letter when you're combining like terms. Okay, in this lesson today, I is not a letter. I is a number. Okay, it's equal to the square root of -1. But if you think of it as a letter, it kind of helps to think about things like this. If you have 2i plus 4i, it's 6i. Kind of like if you did in algebra 2x plus 4x and wrote 6x. Right, so treat I as a letter when you think of like combining like terms. Okay, when we multiply complex numbers together, like if we had, let's say, 2 plus 3i times 8 minus 5i. Okay, we use FOIL, or some people might have learned it as double distributive. So we just multiply just like that. And we'll try an example. When we do division, we're going to use the idea of conjugates. Okay, that's how you divide complex numbers. Okay, you use a conjugate, and you really change it to a multiplication problem. Okay, and last thing we got to make sure we know about is square roots. Okay, when you take the square root of a negative, this is the most common place you see I come up. Right? So the idea is when you have a negative, one way to think about it is like this. Write it as the square root of -1 times x. That's the same thing as -x. And then take and break this square root apart into two separate problems. Square root of -1 and square root of x. And what did we just say the square root of -1 is? How do we represent that?
I squared.
I. So basically what happens when you take a square root is you take the square root of the number you want and you take an I out. Okay, we take that I out because of that negative under the root. All right, let's try a couple. Let's try the square root of -4. Okay, and when you take that I out, generally we put the number and then we put the I after it. The only time you wouldn't want to do that is if you had a problem like this. I would not do something like this. That looks confusing to me. Right? The reason I think that's confusing is I'm not sure if you want this I under the root or you don't want it under the root. So, easy way to clear that up, put the I in front. Yeah, there's no question the I is not under the root. Right? But if you can simplify the number under the root, then we can write it with the I after, because then it would be something like 6i. Does everyone understand the difference between these two? Okay, when you have the root, put it in front so I don't get confused. If you don't have a root, you can write it just like that. Okay? That's how most people, I think, would do it. All right, so how about the square root of -4? Yeah, right?
2i.
Yeah, 2i. It's okay to put the I after it because there's no square root. That's perfect. Okay, James, how about square root of negative 9? 3i. Okay. How about the square root of negative 7? How would we write that one? Yep, Kenny?
That's just I square root of 7.
Yeah, that's all you can do. I square root of 7. And how about the square root of negative 20? Maddie?
2i square root of 5.
Yeah, good job. 2i square roots of 5. Think of it as, if you get stuck, start with the square root of 20, which is square root 4, square root 5. And it's the same thing, except put an I on the outside. Okay. Again, don't put the I after the 5. That's confusing. Perfect. Okay, so any questions on the square roots of negatives? All right. So let's try adding these up. Okay, to add complex numbers, you combine like terms. Combine like terms. You can combine reals with reals. And then you can combine imaginaries with imaginaries. Don't try to take something like 2 plus 3i and simplify it any more than that. You can't. I could do 2i plus 3i, or I could do 2 plus 3, but you can't combine reals and imaginaries. So if I combine my like terms here, first one, my real part is 7, plus real part is 4. What's going to be the real part in the final answer? Jen?
That would be 11.
Yeah, good job. It's going to be 11. Okay, imaginary part, negative 3 in the first term, first number, 5 in the second number. Cameron, if I combine negative 3i with 5i, what do I get? 2i. And that's it. That's how you add complex numbers. Okay, I think that one's simple enough. Let's just go right into subtraction. What do you have to be careful of here? There's a common mistake people make on this one. Yep.
They don't distribute the negative number to the 6 and to the I.
Yeah, you got to remember you're subtracting the 6 and you're subtracting the I. All right, so think of it as 4 minus 6 and negative 2i minus I. All right, so Jacob, what's going to be my real part?
2.
So we've got 4 minus 6.
Negative
2,
2.
yeah. And Leon, my imaginary part?
Negative 2.
Tell me, how are you doing it? What are you doing? What minus what?
I don't really get it.
What's my imaginary part in the first number?
In the first,
Yep, first number.
okay,
Negative
negative 2.
2.
Yeah.
How about in the second?
1.
1.
Yeah.
So we have negative 2, and then we have 1, and what are we doing with them?
Okay, so negative 1. What's your all right.
What are we doing with them?
We have to subtract on one.
What are you doing with negative 2 and positive 1?
Yeah, all right.
Negative 2, positive 1, subtract.
All right. Negative 3.
And what do you put with it?
I.
I. All right. So just make sure you distribute that negative. Does anyone want me to do another one with this subtraction? Okay with that? All right. Let's try a multiplication. Okay, you know that this is multiplication when there's no symbol between the parentheses. You just have 2 sets of parentheses right next to each other. Okay. What's the technique for this one? There's a couple ways some people remember it. Bill?
Foil.
Yeah, you remember it as FOIL or double distributive. So Bill, what would be your first thing you would do?
Multiply the 2 to the 5.
Yep. And what's that?
10.
Good. Perfect. 2 times 5 is 10. Sean, what will be our next thing here?
3 times -1.
So there's different ways you can do. Do you do FOIL?
Oh.
If you don't, you can do it in any order you want, but generally we usually take the first and then we do the outer, usually. But as long as you do them all, that's okay. What would you get if you did the outer here?
-2i.
-2i. Okay, and then Ashley, what would we do next?
3i times 5.
3i times 5, which is how much?
15i.
15i. Okay, now the last part. Okay, be careful here. We have 3i times -i. So the first thing you might want to just start out with, what's a positive times a negative?
Negative.
Negative. Okay, so now it's negative, what's 3i times I, right?
Oh, you could just put it as +3 or just put it as -3i squared.
Yeah, we'll put it as that -3i squared for now. Okay? Does everyone see how we got 3i squared? All right. Now, anytime you have an I squared, you never want to leave that in the final answer. All right? So you gotta simplify that. Let's combine these like terms first. That's going to be 13i. And Dave, what did we say I squared was earlier? Yeah. So change I squared to -1. So 10 plus 13i. John, what's -3? Or, we can do it this way. What's 3 times -1? -3. And now we're subtracting a negative, so that becomes positive. And now I can combine 10 with 3. Okay, just a coincidence that the real and imaginary parts came out the same. That usually doesn't happen. Okay, so any question on multiply? Okay, in Algebra 2, okay, when I teach it, I usually go a lot slower through it, but you guys have already done it once, so hopefully it's just kind of coming back slowly. That's the hope. All right, so last operation we need to know how to do is division. Well, to do division, we're going to use what's called a conjugate. Okay, so if you have a complex number, like a plus bi, and you want the conjugate, all you have to do is change the sign of the imaginary part. That's what that word means, negate. Change the sign of the imaginary part. Don't do anything to the real part. Keep that the same. All right. So if we had the number 3 plus 2i, 2 is the imaginary part, positive 2. I'm going to change the sign of it, and I'm going to write its conjugate. All right. Anyone think they could give me the conjugate of 3 plus 2i? Aiden? It's 3 minus 2i. Yep. That's it. That's your conjugate. Okay. Matt, how about the conjugate of 4 minus 5i?
4 plus 5.
Yeah, just changing the sign of that imaginary part. Okay. Nick, how about the conjugate of 3i?
-3i.
Yeah, -3i. Okay, if it looks kind of weird to not see the real part, we'll put in 0. 0 plus 3i, 0 minus 3i. Okay. And how about 6? What's the conjugate of 6? Okay.
Just 6.
6 stays the same. Okay, the reason it stays the same, think of it as 6 plus 0i. The conjugate is 6 minus 0i. Whether you add or subtract 0, it doesn't change your number. Okay. All right, so any questions on how you find a conjugate? All right. So now we'll look at how we can use that conjugate to do division. All right, so if you want to divide two complex numbers, okay, what you're really going to do is change it to a multiplication problem. Okay, and you multiply the top and the bottom by the conjugate. of what's in the bottom. Okay, so to do division, multiply top and bottom by the conjugate of what's in the bottom. And you'll see why we're going to multiply by the conjugate. That's going to do something very nice to the bottom. And as we go through it, you'll see. Okay, so what would I multiply top and bottom by here? Right?
2 plus 3i.
2 plus 3i. Brian, why didn't I use 5 minus I? That's a conjugate.
Because you have to do it based on the denominator, not the numerator.
Right. Denominator, not the numerator. All right, so what we'll do is FOIL it out. Okay, let's start with the top, and then we'll do the bottom. So you get 5 times 2 is 10. 5 times 3i is 15i, plus another 2i. What's 15i plus 2i? 17i. And then I'm going to get I times 3i. Yeah, would be 3i squared, which is really what? Negative 3. Okay, you don't have to do that all in one step, but at this level, I think you guys should be able to handle that. Okay, 3i squared, 3 times negative 1 is negative 3. All right, let's do the bottom and watch what happens here. 2 minus 3i, 2 plus 3i. Okay. 2 times 2 gives me 4. 2 times 3i is positive 6i. 2 times negative 3i is negative 6i. What just happened there? It cancels out. Right? So I can write it, but I'm just going to cross it out. 6i, negative 6i. When you multiply conjugates, that always happens. That's the point. And the last part. Negative 3i times positive 3i. What would this be? Yeah?
Negative 9i squared.
Okay, yep, so we'll start like that. So we get positive times negative is negative. 3 times 3 is 9. I times I is I squared. And then in the next step, we'll clean this up a little bit.
Mr. Hager, you're forgetting the I squared of f greater than negative 3 in the numerator.
Oh, in the numerator, thank you. Oh, no, we already did it.
It's just that.
Yeah, it would have been 3i squared, but I squared is negative 1. So we already combined it into the problem. All right, so my numerator is, let's see, 7 plus 17i. And my denominator, what's negative 9i squared? 9, because I squared is negative 1. It'll cancel that negative. So I really get 4 plus 9, which is 13. Okay, your last step is just to write it in standard form. Okay, real part and then imaginary part. So to do that, just take each number and put it over 13 separate. Just like that. So the real part is 7/13. Imaginary part, 17/13. On the test, that's what I'll be looking for. Just separate it like I did there. All right. Any question on division? Yeah.
I was actually just going to ask about that last, like how you wrote it. Is it supposed to be that the I is supposed to be separate from the whole fraction, or just stays with the 7 no matter what?
They usually put it right in the middle.
All right.
It's kind of like if you had like y equals mx plus b, and you had like y equals 2/3 x minus 4. You know how they kind of put the x in the middle? I mean, technically you could do this. It's the same thing, but they usually don't. You could do the same thing here. Technically, you could put the I in the top, but they usually just put it right in the middle, just like slope intercept. What's that?
Mine are written sideways, so I just put it with the top number.
The top, that's okay, yeah. If you put it in the top, that's not wrong. Just make sure if you see this on the test, you know it's the same thing as putting the I right after 17. Don't put it in the bottom. That would be wrong. Okay, any other questions on division? All right. So now we can actually find some roots. And if we have to deal with complex numbers, we get a little background on how to deal with it. All right, this is a quadratic. So how many times could it cross the x-axis? It could cross twice. What else could happen? Could cross twice, fine.
It could just like go up and like stop at it and then go back away.
Okay, yep, so you could have it just touch once, kind of like a repeated root. Like if you were to graph x minus 1 times x minus 1, you'd get a repeated root. What else could happen? Autumn?
Not touch it at all.
Could not touch it at all, and we have imaginary answers. Is it possible I have one imaginary answer and one real answer?
Yeah. No, it's not. You need an even number of imaginary.
Right. So for this problem, these are the scenarios that could happen. You could have either two real answers and no imaginary. You could have one real. Okay. Well, it's actually repeated, so it's a repeated answer. So I guess we could just count it as one real. Or you could have that case. You know what? Just to make it simple, we'll do it this way. Even though the case where you only have one answer, it's really like this. It's two answers. It's just the two answers are the same. So it's repeated. Right? So these are the only two cases that can happen. Two real, either distinct or repeated. No imaginary. Or no imaginary, no real, two imaginary. You can't have one and one. I can't do that. All right, how could I figure out what this one is without graphing it? It's a quadratic, so what could I try to do? Yeah?
Factor.
Okay, I could try to factor it. Unfortunately, I don't think that's going to factor. Two numbers that multiply to give me 1 and then add to give me 1. Not going to work. Devin?
Quadratic formula.
Yeah, just use the quadratic formula. Devin, what are A, B, and C in this formula?
All one.
They're all 1. Okay, so just fill it in and see what we get. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Right, so get negative 1 plus or minus the square root of 4 times 1 times 1 is 4. What's 1 minus 4? Negative 3. Okay, we already know we're going to get imaginaries. Okay, just simplify this as much as you can. Square root of negative 3. But Nick, how would that simplify? Yeah, just I square root of 3. Those are your two answers. Negative 1 plus I root 3 over 2 and negative 1 minus I root 3 over 2. So if you graphed it, which case is it going to be? Is it going to cross the x-axis or not going to cross it? It's not going to cross it. Two imaginary roots. Okay. Questions on that? It's a quadratic, nice and easy. Just use your quadratic formula, solve it like you did in Algebra 2. Okay. If you go back and look at the example we just did, you're going to notice the two answers were conjugates of each other. Negative 1 plus I root 3 over 2 and negative 1 minus I root 3 over 2. Okay, I could write it out, make it even clearer. There's one answer. There's your other answer. Does everyone see how those are conjugates? Okay. Any question on how I rewrote it with the separate denominators? Okay. In general, they're probably going to look for that in the homework, and I will be on the test as well. All right, so I probably should have done that. But now it makes it really clear they're conjugates. And that always happens. Always. All right, so if I tell you that, here's an equation. 2 plus I is a root. What else do you know is automatically a root? 2 minus I. Okay, complex roots not only occur in pairs, they occur in conjugate pairs. So if you know one root, you automatically know another one. And if b was equal to 0, well, that's kind of a special case. That would wipe out your imaginary part, and then you'd just have a real answer. Okay, that's a little different. Okay, all the theorems that we've learned, the remainder theorem, factor theorem, and synthetic division, all work with complex numbers. Okay, everything we've done, you can use complex numbers for. Right? It's a little bit of work to show that a complex number is a root using synthetic division. We can still do it. We just have a lot of side work we're going to do. Okay, a lot of foiling and distributing. So I want to show that 1 minus 2i is a root of that. Well, one way to do it is plug in 1 minus 2i for x and do it out. And make sure your remainder is what? 0. That's going to be a pain. 1 minus 2i to the 4th power, you'd have to do this out. Write it 4 times. Okay. And then you'd have to square it, multiply it by 17. Synthetic division is actually going to be easier. It's not hard, it is a little messy to do. So we go. 1 minus 2i is my root. Okay, put my coefficients down. What are my coefficients going to be here? 4. Yep. Good. 0. 17. 14. 65. Okay, so we're hoping to get remainder 0. What's that?
So just had to pick the big
I had
number.
picked them. Yeah, I did. So now, first step is easy. Bring down the 4. Okay, next step's not too bad. We're going to distribute 4 to 1 minus 2i. Okay, what do you get when you do 4 times 1 minus 2i? 4 minus 8i. Okay, now add those up. It's not too bad. Okay, we got a 0 in there. Oh, now it gets a little annoying. We have to multiply 1 minus 2i times 4 minus 8i.
Oh, then you guys do that and then multiply that.
Yeah, we're gonna have to do it 3 times in this problem. All right, so we're gonna get really good at multiplication. Okay, off to the side, I'm gonna do it so we can keep our work kind of neat here. All right, times 4 minus 8i. All right, so we get 1 times 4 is 4. Minus 8 minus 8 is how much? Minus 16i. And what's negative 2 times negative 8? Start with that. Negative 2 times negative 8 is 16. What's I times I? I squared. What's 16i squared? Negative 16. All right, so 4 take away 16. That gives me negative 12 minus 16i. Okay, next step, add these up. We don't have anything to add to the imaginary part. What's 17 minus 12? 5. Right, now we're going to multiply 1 minus 2i. Times 5 minus 16i. How many of these? Oh, not more than one. One or two at most, because they take a while. On the test, I probably wouldn't even give you one with 5 columns, maybe 3. So we'd be done right now. It'd be shorter. Okay, but I just want to practice it. All right, so 1 times 5 is 5. What's negative 16 minus 10?
Negative 26.
Negative 2 times negative 16?
32.
32. I squared?
Negative 32.
Negative 32. What's 5 minus 32?
27.
Negative 27 minus 26i.
Let's go.
You gonna make it? All right. What's 14 minus 27? Negative 13. All right, and hopefully somehow I just get negative 65 here. So when I add it up, I get 0. Okay, last step. Let's see what happens. 1 minus 2i times negative 13 minus 26i. All right, 1 times negative 13. What's 1 times negative 26i?
Negative 26i.
What's negative 2i times negative 13?
Positive 26i.
Positive 26i.
How nice is that?
And what's negative 2 times negative 26?
Positive 52.
Positive 52 with an I squared.
Negative.
Negative 52.
And negative 13, take away 52. Negative 65. Right. So we showed that it is a root. Okay. Again, on a test, you wouldn't have one with 5 columns. At most, I would give you 3. So you would have been done in half the number of foils. Okay. Does everyone understand how you can do it, though, even though it's a pain?
Yeah.
You can do it. It works. Okay. All right. Why? I've asked you this before. Why would an odd degree polynomial always have to have one real zero? Yeah. If you think about the end behavior, odd polynomials either look like this. Something happens in the middle, and they go up. Or one side goes up, something happens in the middle, and the other side goes down. It could take all kinds of twists and turns in the middle, but it's a continuous function. It goes up forever, it goes down forever. It's going to go through 0 at some point, guaranteed. Okay, what are the scenarios I could have here?
You have 3 reals and no imaginary.
Yeah, I could have all 3 reals and no imaginaries, and that covers distinct and not distinct. Okay, you could have 2 repeated, you could have 3 repeated. The point is you could have 3 real, no imaginary. What else?
1 real, 3 imaginary, 2 imaginary.
Or 1 real, 2 imaginary. Could I have 2 real, 1 imaginary? That adds up to 3. No, imaginaries only come in pairs. So that's all that can happen here. Again, this case includes distinct and not distinct. Maybe all 3 are the same, so it just looks like 1. Okay, but that's still 3 roots. They're all the same. Yeah.
Oh, I just realized what I was going to say, but then it would have just come out as one of the ones that was like exactly the same thing, where you have 2 of the same number. That you said
Yeah.
we wouldn't list it possible.
Yeah, you could have 2 of the same number and then 1 that's different, or 3 that are all different. Yeah. All right. So let's find the zeros for this. All right. So if you set it up this way and you go to solve it, okay, you're going to be able to get just the imaginaries. I mean, just the real. Okay, you could add 1 to each side, take the cube root of 1, and you would get what? X equals 1, just positive 1. Okay, so you could get that root that way. Okay, or you could graph it. Use the calculator to help you get an idea where there's a root. So try x cubed plus 1. It's going to go right through 1. We just said that. Wait a minute. Is it negative?
Negative plus 1 is minus 1. Yeah, you type in plus 1.
Oh, good. I typed it in wrong because I was like, something's not right. So now it should go through 1, right? And if we think 1 is a root, we can check it. Type 1 in. Yeah, 1's a root. Okay, so we got that one. Now that I know that's a root, what can I do with it and with this to find the other roots? Yeah, do synthetic division. Okay, put 1 on the outside. What are my coefficients? Yep.
1, 0, 0, 1.
Close.
I don't know.
-1. Okay, so this is synthetic division. This is going to be real fast. Bring down your 1. 1 times 1. 0 plus 1 is 1. 1 times 1 is 1. 0 plus 1 is 1. 1, 1, 0. Yeah. Okay, so now my quotient is x squared plus x plus 1. Now I want to find the roots of that. Well, x squared plus x plus 1, we already did that problem. We already know the roots. Okay? The two roots are -1 plus or minus I root 3 over 2. Okay? We did that earlier. All right, so the other two roots you get, -1. Was it root 3?
Yep.
Was that root 2? So in this case, that's what it was. 1 real, 2 imaginary. Is everyone okay with just go back and look at your problem for this one? What example was it? Example 4. That'll tell you how to solve that. Okay, so not too bad. Okay, so any question on that? All right. So what we could have done, and I mentioned this, move that 1 to the other side, okay, and then it would say x cubed equals 1. Or then if you take the cube root of each side, you can get x by itself. And it says x equals the cube root of 1. Okay, so what we really just found is we found all the cube roots of 1. So the cube roots of 1 are 1, -1 plus I root 3 over 2, and -1 minus I root 3 over 2. Anytime that you have an equation set up like this, x to some power minus 1 equals 0, what you're really doing is finding the nth roots of 1. Or our book calls it the nth roots of unity. And what happens when you're solving it? If it's a square root problem, 2 answers. Cube root, 3 answers. Okay, 4th root, how many answers do you think? James? 4, yeah. 5th root, 5 answers. Okay, so whatever power you're looking at, that's how many answers you should be finding. Let's look at this one. We're going to find the 4th roots of unity. Okay, how would I set that up as an equation like this? Or you know what, if you wanted, even, does everyone have what's on the left here? Set it up like this. What would be my power on x?
X to the 4th.
Yep, x to the 4th. And what would I put after it? -1. That's what you're really solving. Okay, because if you put the 1 on the other side, just watch this step, because I'm going to erase it. You'd have x to the 4th. Take the 4th root of each side. So you're finding all the 4th roots of 1. Not just the reals, but also the imaginaries. Okay. All right. So the way to do this one, this is factorable. Okay, right off the bat, we don't even need to use any kind of rational root theorem. There's no middle term here. So whatever this factors as, it's going to be an x squared and an x squared, plus and minus, and then the same number. So Aiden, what would it be? Yeah, plus 1 minus 1. If you distribute it out, you'd get x to the fourth minus x squared plus x squared minus 1. This is a difference of two squares. You might have learned that back in Algebra 1 or Algebra 2. It's a difference of two squares. Okay, and there's actually something else that can factor up here. One of these can come down another step.
X squared minus 1.
Yeah, this is also a difference of two squares. If you square x, you get x squared. If you square 1, you get 1. So how would that factor, Dominic?
X plus 1, x minus 1.
Yeah, thank you. X plus 1, x minus 1. I think that's as much factoring as you can do. You cannot factor a sum of two squares, only a difference. Okay, set each one of those equal to 0. Okay, let's start with the two on the right. Those are quickest. What would make this second factor 0? Negative 1. Third factor 0? 1. So we have two real. We're going to have two imaginary. Okay, bring the 1 to the other side. And how do we get rid of our exponent on x? Take the square root. And remember, when we take our square root, what do we want to be careful with here? Anytime you take the square root of a number? How many answers should I get here? 2. So what do I need to put? Plus or minus, anytime you take the square root. Okay. And what is the square root of negative 1? I. So there's your 4 answers. Plus I, minus I, plus 1, minus 1. If you took any one of those things I said and raised them to the 4th power, you would get 1. Okay, so some of them are going to be factorable, so you don't need to use your calculator at all. Okay, any question on that one? All right. So we've kind of noticed a pattern here, and I've already brought it up to you. And we'll get to that pattern in a second. But the first theorem we have, the fundamental theorem of algebra, basically says if you have a polynomial with degree greater than 0 and real coefficients, then I guarantee you're going to have at least one complex 0. Okay, if you have a polynomial with degree n greater than 0 and real coefficients, you're going to have at least one complex root. Now remember, is that a complex number? 3? Yes. Complex numbers don't have to have an imaginary part. If you think kind of like I draw a big diagram when I teach it in Algebra 1 or Algebra 2. Complex numbers can have real parts and imaginary. So if something is a real number, that falls under complex. Okay, so complex basically includes every number you've ever learned about. Reals and imaginaries. This theorem, it's in our book. It's good to write it down, but I don't really think it's overly useful. Okay, probably not something you need to focus or spend a lot of time on. The second one is more important. It tells you how to factor something. All right? So if you have a polynomial and your degree is greater than 0, and you have real coefficients, you're going to have n linear factors. So for example, if you were to factor a quadratic, you're going to have 2 sets of parentheses. If you factor a cubic, you're going to have 3. If you factor a quartic, say something to the 4th power, you could break it down into 4 sets of parentheses. So here's an example. This is a cubic, and it factors into 3 sets of parentheses. How would you do that on your own? If I gave that to you on a test and I asked you to factor this, I just wrote factor. It does come out very nice. Okay, so what would be your first step here to try to factor that? Yeah?
I feel like I remember it's the one where you take all the factors of the first and last coefficient.
Yeah, I think that's a great idea. See if there's a rational root here. Turns out every root is rational. But find a rational root. Use your calculator to help you out. Let's say you graph it and you say, yeah, it looks like it goes through -1. What would you do with that -1? Do synthetic division with the -1. This would turn into a quadratic, and it would be very easily factorable. Okay, I wouldn't give you one that you can't factor or you can't find a rational root. Yeah?
I have a question. Does that say f has h linear factors?
If f is a polynomial with degree n and real coefficients, then f has n linear factors. Yeah. Yeah.
Not hard for me to read.
Keep in mind, the factors don't have to be distinct. They can be repeated. So if you were to graph this is a 5th degree polynomial. In this case, all real roots, no imaginaries. And it would go through -1, and it would go through 2. Okay, and we have all kinds of repeated roots here. And the way you can say it is -1 is a 0 of multiplicity 2, meaning it's repeated twice. 2 is a root, or a 0, of multiplicity 3. It's repeated 3 times. So any question on that theorem, linear factorization theorem? At least it gives you an idea of how many factors you should be looking for, depending on the degree of your polynomial. All right, so the last one, we're not going to go through it. It looks bad, but it actually, when you find one root and divide through it, a whole bunch of stuff cancels out, and it factors right away and you're done. So even though it looks kind of bad, it's actually very simple because of the numbers they picked. In general, a 5th degree polynomial could be awful. It could be really bad. This is easier than some of the other ones we did today. Okay, but we're not going to go through it. All right. So any questions on anything we did today? We did a lot of stuff, kind of review with the first half, though.
Okay, I just have a quick question. What do you mean that 1 is a 0, multiplicity 2, and 2 is a 0, multiplicity 3?
It's how many times the root is repeated. So like in this problem, it's repeated twice. Or 2 is a root, but it's repeated 3 times.
Wait, so when you say that, do you mean like, so like if something has a 2, like x minus 2 to the second, then you say, like, oh, what do you, well,
2 makes this factor 0, makes that factor 0, and makes that factor 0.
So is that just
Yeah.
talking about that problem alone?
Yeah, it's just that particular problem.
Okay, so it's not just a rule in general?
No.
Okay.
No, one is a root here just in this problem. Yeah. 2 is a root just in this problem. Is that clear? This is specific to the example right above it. Yeah. Yeah. Good point. That's a good question. Any other questions? All right. So the homework, it's on 193. It's 1 through 3, 8, 9 through 13, that says 15, 19 to 22, 25 to 27, and then 32, 36, 39, 40, and 47. Right, so tomorrow we'll go over that before the test. If there's any other questions, we can review, and then we'll do our test.